In this example, you will analyze an electrokinetic sample injector that is used to transport well-defined sample volumes of dissociated acids and salts. The model is made up of two channels, the horizontal, focusing channel, and the vertical, injection channel. Additionally, there are two stages within the model, the focusing stage and the injection stage. This particular video will describe the focusing stage, in which a fluid containing the ionic species flows from left to right in the horizontal channel, driven by a pressure gradient. Pressure-driven flows also inject buffer solution into the horizontal channel from both the upper and lower vertical channels, leading to a focused concentration profile at the junction. The second stage of the device operation will be shown in a follow-up video. In this stage, the pressure-driven flow is turned off and an applied electric field drives the ionic species from the focusing zone into the vertical injection channel. Two modes of operation are demonstrated, Mode A and Mode B, which differ only by the electric field boundary conditions. In the Model Wizard window, select 3D as a space dimension and click Next. From the AC-DC node, add electric currents. From the Chemical Species Transport node, add a transport of diluted species. And from the Single-Phase Fluid Flow node, add a creeping flow. Once the physics is selected, choose Stationary as your study type and click Finish. The first stage of this model is stationary because we're solving for the steady-state condition. The solution of this stage will then be used as the initial condition of the injection stage, where the fluid physics will be time-dependent. Right-click on the Global Definitions node and add a parameters list. In the Parameters section, define parameters for the average velocity of inlets, the sample ion diffusivity, temperature, sample ion concentration, and charge number. To add the geometry, we're going to use the import function. Click Browse and find the Model Library folder. Select Electrokinetic_valve.mph bin, click Open, and select Import to load the valve. Now you can build the model. Right-click on Materials node and add a material. In the Material Contents section, define the material properties as seen. From the Electric Currents node, add an electric potential. Using the Paste Selection button, add boundary 1, then define V0 as having an induced voltage of -1 volts. Add a ground node to the opposite side of the channel and select boundary 54. This will create a potential pushing the negatively charged ion samples from the sample inlet to the focusing channel outlet. On the top of the Model Builder window, click the Show button and select Discretization. This step will allow discretization sections to show on the platforms you're working on. In the Transport of Diluted Species node, check the Migration and Electric Field checkbox to specify the mobility and charge number. Expand the discretization section and from the concentration list, choose Quadratic. In the Convection, Diffusion, and Migration node, enter T as the temperature, D as the diffusion coefficient, and Z_C as the charge number. In the Model Input section, under Velocity Field, choose Velocity Field, and under Electric Potential, choose Electric Potential. Right-click Transport of Diluted Species and add a concentration at Inlet Boundary 1. Check the Species C checkbox to define the concentration of the species coming in at the boundary as C_N. Add another concentration node, but this time select boundaries 21 and 26. Again, check the Species C checkbox and leave the field as 0 such that no concentration of the sample is added through those boundaries. Right-click Transport of Diluted Species to add an outflow at boundary 54. Now define the properties and boundaries of the creeping flow by adding an inlet and selecting boundary 1. Choose laminar inflow as the boundary condition. Define the average velocity as u_a and the entrance length as 100 micrometers. Right-click Creeping Flow and add a second inlet. This time, select Boundary 21. Similarly, select laminar inflow as a boundary condition and type w_a as the average velocity with 100 micrometers as the entrance length. Add a third inlet to the creeping flow and select Boundary 26. Choose laminar inflow as a boundary condition and w_a as the average velocity with an entrance length of 100 micrometers. Now add an outlet to the creeping flow node and select Boundary 54. Moving on to the mesh settings, add a free tetrahedral mesh. In the Mesh 1 Size node, choose Find as the predefined element size, then build the mesh. To run our simulation, we'll have 3 sequential solver steps, each solving for one of the physics that has been previously defined. Add a second study step by right-clicking on Study 1 and selecting Study Steps, then Stationary. Similarly, add a third stationary study step. For Step 1, leave only the creeping flow physics enabled. For Step 2, leave only the electric currents physics enabled. And for Step 3, leave only transport of diluted species physics enabled. Right-click on Study 1 and compute the model. Once the results are calculated, expand the concentration node and select Slice 1. Choose Z-X planes from the plane list and plot only one plane. In the expression section, choose Replace Expression, then choose Transport of Diluted Species, Species C, and select Concentration. Click Plot to see the new slice. This graph illustrates the concentration of the sample into the buffering solution during the focusing stage. Now, to make the plot more illustrative, add an error volume. Click Replace Expression and choose Creeping Flow, then Velocity Field. In the error positioning section, set the X grid points to 28 and the Z grid points as 10. Enable the Scale Factor checkbox and change it to 0.006. Then plot the graph again. In this figure, you're able to visualize the sample concentration as a function of the fluid flow. The magnitude and direction of the flow field is demonstrated by the direction and length of the arrows respectively. Watch Chapter 2 Injection Stage or visit our website for more information on this model.